We are going to begin today with a number that is designed to make you feel very small. The number is 1 chance in 10 to the 164th power. It is a figure popularized by the author Stephen Meyer in his book Signature in the Cell, and it represents his calculation for the odds of a single functional protein of a modest length, say 150 amino acids, arising by random chance in a prebiotic soup. When you encounter a number of that magnitude, the human brain simply gives up. We do not have the cognitive architecture to process a denominator with 164 zeros. To put it in perspective, physicists estimate there are only about 10 to the 80th protons, neutrons, and electrons in the entire observable universe. So Meyer is telling us that finding this functional protein by chance is essentially smaller than finding one marked subatomic particle among all the matter that exists many trillions of times over. This is the cornerstone of what we might call the information-first improbability argument against abiogenesis. The argument insists that first life required a massive influx of functionally specified biological information before any mechanism like natural selection could even begin to operate. And because this target is so astronomically rare in the combinatorial space of all possible amino acids, prebiotic chemistry is framed as nothing more than blind chance searching an infinitely dark room. The logical conclusion, if you accept this framing, is that unguided physical processes are wholly inadequate, and therefore design is the best explanation. I want to spend a very long time unpacking why this argument is profoundly persuasive to so many intelligent people, and why it is mathematically, physically, and philosophically incorrect. It fails not because the math of permutations is wrong, but because it computes the wrong event. We are looking at a caricature of origin. The event at issue is not the one-shot appearance of a finished modern protein. We must stop treating the origin of life as a single lottery ticket drawn from an abstract sequence space. Matthew Tripp Zeta, in a seminal March 2026 paper, targeted this exact family of anti-abiogenesis arguments. He proposed replacing this flawed probabilistic model with what he calls the resolution state interface, or RSI. Zeta argues that the relevant event is a staged physical process over admitted intermediate states on real carriers under real gradients with real cycle structure and real retention boundaries. Once you write the problem that way, the key probabilistic move in Meyer's argument no longer tracks abiogenesis. It tracks a phantom. We need to examine the genealogy of the one-shot draw illusion. Where did we get the idea that nature operates by throwing all the biochemical dice at once? Historically, we have always struggled to model gradual, cumulative processes that lack an intentional designer. When we look at a modern cell, we see a marvel of integrated technology. We see transcription, translation, error correction, and a coded molecular system that resembles human software. Our intuition, shaped by our own experience as toolmakers, demands that such an apparatus must have been assembled whole, or at least that its most fundamental components, like a functional protein, had to cross a vast chasm of improbability in a single leap. But nature does not build finished components in a vacuum. Nature builds through constraint. The one-shot model assumes a flat, uniform landscape where every possible combination of amino acids is equally likely, and where chemistry has no preference, no bias, and no memory. It assumes that an environment before Darwinian selection is an environment devoid of physical sorting. This is a catastrophic conceptual error. Prebiotic chemistry is already strongly structured before selection ever enters the picture. The Earth did not offer a single miraculous instant for life to appear. Geology tells us something entirely different. We have evidence of continental crust and liquid oceans by roughly 4.4 billion years ago. We have conservative evidence for life in the Dresser Formation by about 3.48 billion years ago. That leaves a conservative window of nearly 1 billion years. 1 billion years of active, churning, repetitive planetary chemistry. This is not a single blind draw. This is an immense, structured opportunity space. We must linger on this distinction. The difference between a one-shot draw and a constrained, staged path is the difference between trying to phase through a brick wall and walking up a flight of stairs. Meyer's model asks the atoms to phase through the wall. Zeta's model maps the stairs. And yet the information-first argument stubbornly persists because it relies on a very specific definition of information, one that demands a final, recognizable function before any credit is given to the process. If a sequence does not fold into a modern, useful protein, it is discarded as a failure. But early life did not need modern proteins. It needed minimal, persistent organization. It needed something that could survive, reproduce its class, and maintain a boundary. We are going to deconstruct the entire edifice of this improbability claim, brick by brick, and replace it with a mechanism that honors the actual physics of early Earth. Let us delve into the technical mechanics of the false finish target. When you hear that probability of 10 to the negative 164, you must ask yourself what exact mathematical operation produced that figure. It is derived from calculating the fraction of functional sequences within the total combinatorial space of all possible sequences of a given length. You take the number of arrangements that fold into a working protein and divide it by the number of all possible arrangements. This is what Zeta terms the one-shot target model. The equation is elegant. The equation is simple, and the equation is useless for biology. Why? Because the actual physical process of abiogenesis is not supported on a uniform measure of finished targets. Chemistry does not sample abstract sequence space. Chemistry moves through local transitions on real carriers. Think about the concept of a carrier for a moment. In the abstract mathematical space Meyer uses, an amino acid chain is just a string of letters. But in reality, an amino acid chain is a physical object interacting with its environment. It might be clinging to a mineral surface. It might be trapped in a microscopic pore in a hydrothermal vent. It might be drying out on a sun-baked rock and then re-wetting in a tidal pool. These physical realities are what Jida encodes in his resolution state interface. RSI forces us to ask two physical-level questions at each stage of development. First, is a given intermediate state actually admitted on its actual carrier, not floating in some abstract soup? If a state fails the existence gate, it is lost, regardless of how promising its sequence might look on paper. If it clears the existence gate but fails the change gate, it simply persists without advancing. A state that clears both becomes a candidate corridor segment in a real historical path. This fundamentally alters the mathematics of the origin problem. It shifts the focus from a target-based search to a path-based, carrier-based, and stage-based progression. When you integrate these constraints, the sheer vastness of the search space collapses into highly directed corridors of probability. We must interrogate the assumption that intermediate states without final modern function are useless. The information-first argument claims that unless a sequence performs a specific recognizable biological task, it cannot systematically narrow the search for future states. This is empirically false. A sequence does not need to be a perfectly folded enzyme to change the physical landscape. It might simply be sticky. It might alter the local pH. It might recruit other molecules to a mineral surface, effectively increasing their local concentration by orders of magnitude. These mundane, non-biological physical effects create biases. They open corridors that did not exist before. They change the baseline transition intensities for the next chemical step. We have experimental proof of this. Consider amino acid-assisted RNA copolymerization. Researchers have found that amino acids can promote RNA formation by more than 100-fold under ambient alkaline conditions. This is a massive, localized gain factor. It is not Darwinian selection. It is a pure chemical bias that widens the transition corridor long before anything resembling a modern cell exists. The information-first model ignores this entirely. It treats every step as an independent, unbiased roll of the dice. By doing so, it artificially inflates the improbability of the outcome. It is a mathematical sleight of hand that substitutes a sterile, uniform probability space for the messy, constrained, and highly biased reality of planetary chemistry. If we are to understand abiogenesis, we must discard the illusion of the finished target. The first lifelike threshold was not a fully coded molecular system. It was merely the first bounded chemical organization capable of persistent throughput, regenerative closure, and minimal heredity. That is the target we should be calculating. And when we do, we find that the universe is far more accommodating to life than the one-shot model would have us believe. We arrive at the shadow side of probability. There is a deep psychological comfort in framing the origin of life as a binary opposition between chance and law, or, as Meyer does, suggesting that if chance and law fail, design must be the victor. This framing provides a false sense of closure. It implies that we have mapped all the causal categories available to the universe. But this is a gray area that resists such neat categorization. What happens when we look closely at the phrase chance plus law? In the public discourse, law is usually reduced to simple, repetitive physical constraints like gravity or basic chemical valency. Chance is reduced to blind, unweighted randomness. But non-equilibrium thermodynamics does not fit cleanly into either box. A hydrothermal vent complex is not a random number generator, nor is it a simple deterministic clock. It is a structured environment that continuously pumps energy and material through microscopic compartments, creating massive local gradients. These gradients force chemistry to explore specific, highly biased pathways. Is that chance? Is that law? The terminology itself betrays our ignorance. We rely on the word chance when we are too lazy to model the constraints. The shadow side of the information-first argument is that it uses probability not as a tool for discovery, but as a weapon for obfuscation. By insisting on computing the probability of a finished target without the intervening physical constraints, it guarantees a microscopic result. It then uses that microscopic result to declare the process impossible. But the impossibility is an artifact of the model, not a feature of the world. Think about the concept of a retention boundary. In a vast open ocean, any complex molecule you synthesize will quickly diffuse away. The concentration drops to zero, and the chemical reaction stops. The probability of building a long polymer in an infinite ocean is effectively nil. The information-first model implicitly assumes this infinite, unconstrained ocean. But Earth is not an infinite, featureless ocean. It is covered in pores, cracks, ice channels, and lipid vesicles. These are retention boundaries. They trap molecules. They prevent diffusion. They allow concentrations to rise dramatically. In porous niches near hydrothermal vents, we measure average enrichments of 40-fold and up to 130-fold in the deepest parts of the pore. Heat flows through these cracks can enrich and separate more than 50 prebiotically relevant organic compounds. Heat flow-driven phosphate processing can boost trimetaphosphate formation by 260-fold relative to thermal equilibrium. These are not minor adjustments. These are massive compounding gain factors that fundamentally rewrite the local probability measure. When you ignore retention boundaries, you are not doing rigorous science. You are doing a parlor trick. You are calculating the odds of a sandcastle spontaneously assembling in a hurricane while ignoring the fact that the universe has provided buckets, spades, and wet sand. The gray area here is how we quantify these compounding biases over geologic time. We cannot easily point to a single moment and say, here is where chemistry became biology. The boundary is smeared out over millions of years and billions of microscopic chambers. The transition is a slow accumulation of localized gains, a gradual tightening of constraints, a creeping increase in persistence. We must resist the urge to resolve this complexity by appealing to a discrete miraculous intervention. The shadow side demands that we sit with the discomfort of a slow, messy, heavily biased process that slowly bootstraps itself into existence without a master blueprint. I want to formally introduce the architecture of Matthew Tribb Zaida's resolution state interface because it offers a precise language for this messy reality. Zaida recognizes that we cannot simply wave our hands and invoke gradients and carriers without mathematically defining them. RSI provides that definition. It starts with ledger primitives. We have the field side budget, which represents the total local driving energy from gradients, cycling, or redox flow. We have the anchored energy, which is the energetic support of the present state, normalized by the layers of the system. The sum of these is the explicit positive ledger. Zaida refuses to invoke hidden negative wells or magical reservoirs. Everything must be accounted for locally. From these primitives, we derive the gates. The existence gate asks if the anchored energy is sufficient to maintain the state on its actual carrier interface. The actual carrier interface could be a mineral surface, a pore wall, an ice channel, or a vesicle boundary. It is a physical, localized constraint. If the state cannot be supported on the carrier, it diffuses away or breaks apart. It ceases to be part of the path. If it survives the existence gate, it faces the change gate. The change gate measures the field side drive relative to the anchored state. It asks if there is enough local forcing to push the system into a new, adjacent configuration. It is a measure of becoming, of transition. This is a profound shift in perspective. We are no longer asking, what is the probability of the sequence? We are asking, is this specific molecular arrangement currently anchored to a rock, and is the surrounding chemical gradient strong enough to add another piece to it? If both gates are cleared, we have an admitted transition. We have taken one step on a physically viable path. Zaida then takes these symbolic gates and translates them into observable, measurable quantities. This is where the model leaves the realm of pure theory and becomes a calibration tool for empirical science. He defines the active lifetime of a niche, the effective cycle time of that niche, and the number of admitted trial windows. He incorporates measured empirical gain factors like the 100-fold amino acid boost or the freeze-thaw amplification rates. He includes a retention factor, measuring how much useful structure remains after dilution or washout. All of these combine to form a local bias multiplier. This multiplier is not a guess. It is derived from direct experimental measurements of prebiotic chemistry under realistic conditions. When you assemble this repaired model, you define an integrated opportunity count. This is the time-integrated, admitted transition opportunity accumulated across all stages within a specific, long-lived niche. From this, you calculate a niche probability. This is the correct way to approach the mathematics of origin. It is disciplined. It is grounded in geology and thermodynamics. It forces you to state your assumptions clearly. If you want to claim that abiogenesis is impossible, you must do it within this framework. You must show that the local bias multipliers are too small, or the retention factors are too low, or the number of trial windows is insufficient. You cannot simply point to a one-shot target probability and declare victory. Zaida's RSI model systematically dismantles the information-first argument by showing that its foundational premises are physically meaningless. It exposes the target space ratio as a mathematical ghost, haunting a landscape that actual chemistry never visits. Let's think about carriers and the physical persistence problem through a grounded lens. I want to spend some time looking at the humble wet-dry cycle. The information-first argument frequently relies on the caricature that prebiotic chemistry has no reliable mechanism to produce long polymers. In an unstructured aqueous environment, the equilibrium heavily favors hydrolysis. Water breaks polymers apart. To build a long chain of amino acids or nucleotides, you have to extract water from the system. In a continuous oceanic soup, this is a severe thermodynamic bottleneck. But the Earth is not a uniform bathtub. It has tidal zones, hot springs, and shallow pools that are subjected to relentless cycles of evaporation and rewetting. Consider a mineral surface at the edge of a geothermal pool. During the day, the sun and the geothermal heat evaporate the water. The dissolved organic molecules are concentrated into a thin, drying film on the mineral surface. As the water leaves, the thermodynamics flip. Dehydration synthesis becomes favorable. The molecules are physically forced into close proximity, and the removal of water drives them to link together, forming polymers. This is not a theoretical model. This is an observed phenomenon. Song and co-authors recently demonstrated that wet-dry cycling drives mononucleotides into long nucleic acid chains, producing oligomers up to 53 nucleotides in length, with abundant species at 35 and 43 nucleotides. This result is devastating to the one-shot probability model. It proves that iterative physical cycling on a real carrier can generate substantial polymer length without postulating a fully modern translation system, without a pre-existing genetic code, and without an intelligent designer pulling the strings. The drying film is the actual carrier. It provides the existence gate, anchoring the molecules and concentrating them. The heat and dehydration provide the change gate, driving the polymerization reaction. When the pool re-wets, the new, longer polymers are redissolved. Some may be lost to hydrolysis, but some will persist. The next drying cycle concentrates them again, perhaps bringing them into contact with new monomers or other polymers, facilitating further growth or complexation. This is the stage-by-stage physical process Zebja is talking about. It is a slow, rhythmic breathing of the environment, mechanically ratcheting the chemistry toward higher complexity. Every wet-dry cycle is an admitted window, an opportunity for the local ledger to drive a change. And the Earth provides billions of these windows. The persistence problem is solved not by a magical one-time event, but by the relentless cyclical nature of planetary mechanics. The environment itself acts as a massive distributed engine for polymer synthesis. When we observe these systems, we see that the physical structure of the environment is deeply implicated in the chemical outcome. The shape of the pool, the mineralogy of the rock, the temperature of the air, the frequency of the tides, all of these dictate the local bias multiplier. The chemistry is not searching an abstract space. It is navigating a highly specific, physically constrained labyrinth, and the walls of that labyrinth actively guide the molecules toward complex organization. The failure of the information first argument is its refusal to see the labyrinth. It looks only at the starting materials and the final product, and concludes that the distance between them is unbridgeable. It ignores the winding cyclical path that the environment explicitly provides. We must now interrogate the technical mechanics of amplification, specifically looking at environments that seem profoundly hostile to life, freeze-thaw brines. When drying pools provide a mechanism for polymerization, freezing environments provide a mechanism for stage local replication and gain. When water freezes, it forms a pure ice lattice. Any dissolved salts or organic molecules are excluded from the growing ice crystals and concentrated into microscopic liquid veins and brine pockets between the ice grains. This freezing process acts as a massive concentrator, drastically increasing the local density of reactants. But it does something else, something critical for the emergence of heredity. In a freeze-thaw system, we find measurable, repeating amplification. Atwater and colleagues studied a polymerase ribosome under pH freeze-thaw cycling. They found that this system supports an open-ended exponential replication phase. They measured per-cycle gains of 1.20 and 1.38 for the two product strands. Over a 4-cycle exponential phase, the total amplification reached factors of 3.5 and 7.0 from the starting duplex. I want you to hold those numbers in your mind: 1.2, 1.38. A 7-fold total amplification. These are not invented probabilities. These are measured, empirical multipliers on a local change corridor. They represent actual replication happening in a structured, abiotic environment. In the context of Zejda's model, these numbers are profound. They calibrate a stage local transition intensity. In a coarse-grained model, you treat these values as empirical multipliers without needing to pretend you have solved the entire origin pathway. When you apply a multiplier of 1.38 per cycle across thousands of freeze-thaw cycles, the local measure of probability is completely transformed. The system is heavily, violently biased toward replication. The information-first argument suppresses this kind of data. It relies on the assertion that before a fully integrated modern cell exists, there can be no significant amplification or selection-like dynamics. It insists that chemistry must remain blind and unbiased until the whole machine is assembled. The freeze-thaw brines prove this assertion false. They demonstrate that pure, physical cycling can drive exponential amplification of complex molecules. The ice channel is the actual carrier. The freezing process provides the concentration and the compartmentalization. The thawing provides the mixing and the reset. The cycle itself is the engine of gain. When we combine this with the polymerization driven by wet-dry cycles and the purification driven by hydrothermal heat flows, we begin to see a network of intersecting physical engines, each contributing its own local bias multiplier. The Earth was not a passive stage waiting for a chemical miracle. It was an active, churning factory of complexification. The probabilities do not lie in the abstract sequence space. They lie in the physical properties of water, ice, rock, and heat. They lie in the specific thermodynamics of phase transitions and chemical gradients.
When you rigorously account for these physical engines, the astronomically tiny probability calculated by Stephen Meyer evaporates. It is replaced by a physical inevitability, grounded in the relentless iterative processing of matter by planetary energy flows. We must abandon the math of the casino and embrace the math of the geyser, the tide, and the glacier.
How does this shift in understanding ripple outward into our broader cultural consciousness? For decades, the public has been fed a narrative of profound cosmic loneliness, heavily reinforced by improbability arguments. If the origin of life is a one-shot draw of 10 to the negative 164, then we are an unfathomable anomaly. We are a rounding error in a dead universe. This perspective breeds a specific kind of existential fragility. It suggests that life is unnatural, a bizarre departure from the normal thermodynamic order of things. It feeds the notion that we are separate from the universe, placed here by an external designer because the cosmos itself is hostile and sterile. But Zeta's RSI model and the empirical chemistry it relies upon shatters this narrative. It forces a cultural realignment. If life is not a miraculous accident, but a staged, constrained admissibility problem driven by ubiquitous planetary mechanisms, then life is a natural expression of the universe. When you have billions of rocky planets with water, heat flows, and wet-dry cycles, the emergence of bounded, complex chemical organization is not an anomaly. It is an expected thermodynamic outcome. This redefinition of life's rarity changes how we view our place in the cosmos. We are not strangers in a strange land. We are the land waking up. The minerals, the water, the thermal gradients, these are not just the backdrop for life. They are the parents of life. The chemistry that runs in our cells is a direct, unbroken lineage from the geochemistry of the early Earth. This perspective offers a profound sense of belonging. It grounds us in the physical reality of our planet. We do not need to look for a ghost in the machine. The machine itself, the vast, churning planetary engine, is sufficiently magnificent. The cultural ripple effect of defeating the information-first argument is a movement away from supernatural exceptionalism and toward a deep physical integration with the natural world. It demands that we respect the intricate, delicate physical systems that gave rise to us, because those same systems are what sustain us. The probabilistic defeater is often used to prop up a specific theological worldview, one that requires a meddling designer to bridge the gaps in nature's capabilities. By showing that nature has no such gaps, only staged, constrained pathways, we do not banish wonder, we relocate it. We move the wonder from the realm of the invisible and the miraculous into the realm of the tangible and the measurable. We find wonder in the fact that a hydrothermal pore can concentrate molecules 100-fold. We find wonder in the fact that freezing water can drive exponential replication. The universe does not need to be broken and fixed by a designer to be beautiful. It is fundamentally, structurally predisposed to generate complexity. This is a far more robust and comforting worldview than balancing our existence on a vanishingly small mathematical improbability. It tells us that we belong here, and that the universe is teeming with the same potential. Let us move deeply into the mechanics of gradients, compartments, and the profound power of the weight. The information-first model suffers from an acute lack of patience. It demands a finished protein immediately. But natural systems utilize vast stretches of time, not as empty voids, but as active opportunity substrates. Consider the alkaline hydrothermal vents, similar to the lost city field. These are not the super-hot black smokers, but cooler, longer-lived structures. A single lost city-style complex can vent for over 120,000 years. Within that complex, there are roughly 100 billion microscopic chambers per cubic meter. When you multiply the chamber density by the volume of the complex and the lifetime of the field, you get an opportunity substrate of at least 10 to the 17th chamber years, 100 quadrillion chamber years of structured confinement in just one vent system. This is what Zeta means when he says probabilistic resources must be counted in carriers and windows, not in abstract sequence draws. These microchambers are bathed in a continuous flow of fluid, maintaining a steep pH gradient. The fluid venting from the Earth is alkaline, around pH 9 to 11, while the surrounding Hadean Ocean was mildly acidic, around pH 6.5 to 7. This difference in pH across a thin mineral barrier is a massive source of free energy. It is a natural proton motive force, remarkably similar to the chemiosmotic gradients that drive ATP synthesis in every living cell today. The chamber wall acts as the existence gate, retaining the molecules and preventing them from washing away into the dilution of the open ocean. The pH gradient acts as the change gate, providing a relentless, continuous push, driving carbon fixation and complex organic synthesis.
You and colleagues have shown that even minimal protocells with simple fatty acid membranes can maintain proton gradients and support ATP synthesis under these vent-like conditions. The physical environment provides the exact architecture needed to bootstrap energy metabolism. The compartment focuses the reactants, the gradient provides the power, and the geological timescale provides the necessary patience. This is the opposite of a random search. It is a highly localized, massively parallel, continuous flow reactor operating under strict thermodynamic constraints for hundreds of millennia. When you drop a generic 10 to the negative 164th probability into this environment, it shatters. The model is completely decoupled from the physical reality of the vent. The vent does not roll dice. The vent forces molecules into specific configurations because those configurations are thermodynamically favored under the local gradient. If a pathway is favored, its probability approaches 1 regardless of how complex the final product appears to an outside observer. We have to learn to respect the physical structure of the weight. Time is not just a multiplier for random chance. Time is the medium through which persistent local biases accumulate into macroscopic organization. The hydrothermal vent shows us that the universe is an engine for generating structured opportunity, and it has all the time it needs. We arrive at the shadow side of the word information itself. Why is the information first framing such a linguistic trap? Meyer and others use the term functionally specified biological information as if it were a physical substance, a magical ingredient that must be injected into the system from the outside. They draw an analogy between DNA and human computer code. Because human code requires a conscious programmer, they infer that biological code must also require an intelligent designer. This is a fatal category error. Human information is abstract. It exists independently of its physical medium. A string of code means the same thing whether it is written on a hard drive, printed on paper, or spoken aloud. The medium is arbitrary. Biological information is fundamentally different. It is entirely physical. It is not abstract code. It is stereochemistry. A sequence of RNA does not contain information in the way a book contains a story. A sequence of RNA has a specific three-dimensional shape, a specific distribution of electrical charges, and a specific thermodynamic stability. When it interacts with another molecule, it does so through physical docking and chemical bonding, not by reading an abstract script. When we use the word information to describe this, we are applying a human metaphor to a chemical process. The metaphor is useful for our own understanding, but it becomes a trap when we mistake the map for the territory. The information first argument confuses the human description of the system with the physical requirements of the system. It assumes that because we need intelligence to write computer code, nature must need intelligence to build a specific stereochemical sequence. But nature does not write code. Nature explores physical constraints. Zeta's model dismantles this trap by refusing to use the word information as a primitive cause. Instead, he speaks of persistent carriers, throughput, regenerative closure, and minimal heredity. A molecule that acts as a template for its own replication is not passing on information. It is physically constraining the formation of the next molecule. The specification is not an abstract command. It is the physical shape of the template. By demanding that fully formed information exist before selection can operate, the public argument creates an impossible paradox. It demands the end product before the process has begun. But if we recognize that what we call information is just a post hoc human description of physical constraint and chemical memory, the paradox dissolves. The system builds physical constraints gradually, step by step, carrier by carrier, cycle by cycle. The information is not injected, it is physically accumulated through the relentless filtering of the existence and change gates. We have to purge our language of these abstract ghosts if we are to understand the physical reality of origin. The chemistry is enough. The thermodynamics are enough. The physical shape of the molecules is the only information the system requires. When we let go of the linguistic trap, the universe reveals itself not as a coded simulation, but as a deeply physical, self-organizing reality.
We are reaching the culmination of this immense architectural deconstruction. We have torn down the one-shot combinatorial model. We have replaced it with Zejda's resolution state interface. We have grounded our probabilities in wet-dry cycles, freeze-thaw brines, and hydrothermal vents. We have exposed the linguistic traps of chance, law, and information. We are left with a universe that is far more fertile, far more active, and far more physically constrained than the improbable lottery we were told to fear. The final piece of this puzzle is the many worlds inevitability. I am not invoking astronomy to rescue failed local chemistry. I am stating what happens when you combine successful, constrained local chemistry with the staggering scale of the cosmos. The NASA Exoplanet Archive currently lists over 6,000 confirmed exoplanets, and conservative estimates suggest the Milky Way alone contains at least 100 billion planets, likely averaging one or more per star. When you apply Zejdah's path-based probability, a probability grounded in billions of years, billions of niches, and massive local bias multipliers, to a galaxy containing hundreds of billions of planetary laboratories, the math shifts from possible to inevitable. Theorem 2 in Zejdah's work states this explicitly. If the local path-based origin remains non-zero under a calibrated model, then large multiplicity drives the ensemble probability close to unity. It is a mathematical certainty. The universe is not a sterile void occasionally interrupted by a miracle. It is a vast, distributed engine designed by the laws of thermodynamics to generate complexity wherever the constraints allow. The defeat of the information-first argument is not just a victory for rigorous chemistry. It is a profound reclamation of our origin story. We are not aliens placed on a hostile rock. We are the rock itself, complexified through billions of years of wet-dry cycling, freezing, thawing, and hydrothermal pumping. We are the inevitable consequence of a universe that relentlessly explores the corridors of physical constraint. We no longer need to cower before numbers with 164 zeros, because those numbers belong to a phantom universe that does not exist. We live in a universe of carriers, gradients, and gates, a universe that actively builds towards life. I invite you to share this perspective. If this careful dismantling of the improbability myth resonates with you, pass this audio along to someone else who might be wrestling with these deep questions of origin. Share it listener to listener. Let us build a culture that understands its deep physical roots, a culture that finds its wonder not in the impossible, but in the magnificent, constrained inevitability of the real world.